So in order to do finish up quantum mechanics, we have to talk about what we've done so far. Okay. To be fair, we're going down the rabbit hole. So let's just keep going there. We've got this. The way quantum mechanics starts, we try to figure out what an electron is. What an electron is, how big is it, what is going on. We can find its mass, we can find its charge. Those are indisputable and easy to find. When we started to try to figure out what its diameter is, by squishing it with all the different tools we could find, it didn't want to let us know that. Why? Because again, when you have an electron, and in order to find where it is, you're going to have to shoot it with a light beam. Shoot with a light beam is the only way you can find an electron. The electron, if it gets hit by it, is going to go poof, gone, right? It's going to be out of there. The problem with that piece is, well, if you hit it with a really big wavelength, you don't know where it was to begin with. It may not get hit very hard, but it's going to move. And so you've got uncertainty. You got uncertainty how it's going, and or you have uncertainty where it is. Because you have uncertainty in both. Again, if you hit it with a lower wavelength thing, the higher frequency, you're hitting with a lot more energy. So although you got a better location than initial, you're going to blow it the heck out of there. And so you're not going to show where it is or how fast it's moving. It's going to be even harder to figure out. Okay? So that was the situation with Heisenberg. So Heisenberg comes up with this idea, well, you're just never going to figure that out. Why? Because all you can do is use light to find it, and light has this limitation. You can squish one, but the other, if you squish the other one, you get bigger. So somewhere between speed and displacement is our problem. We can't figure out with those two together. If you increase the clarity of one, you're going to lose the clarity in the other. And he actually came with an equation that we use today. And that was all good. Nobody's going to, oh no, the worst problem was not knowing where it was led physicists to do experiments. And the experiments started to do things they didn't like. The two-slit experiment, the single-slit experiment, two-slit with the wire. And the problem is this: they were discovering things that acted like the probability. So they would do the probability wave, like it's coming through both slots of the two-slit experiment. But then the electron, instead of acting like it was some probability coming through one, it would act like it's coming through both, half-z, and then it would start interfering with each other because the electrons don't like having like half electrons, so they start separating. These waveforms start pulling apart as if one half went through the other. And that changed the moment you did an experiment to determine which one it went through. And this was disturbing. It was like, well, how does this? So the answer to the question from Einstein is, look, we're still just making bad measurements. And if you want to live in a world where that's true, you can pretty much, say they're just wrong. The experiments we've been doing for the last 50 years don't amount to much. We don't know what the data is going in, so we can't going out. So the probability is just error carried forward. Problem with that information is we have repeatedly, because physicists are human beings, we don't like the fact the universe an electron doesn't have a place. We don't like that at all. We want to know where the electron is. The electron has to be in a spot. And what we discovered is the electron does not have to be in a spot. The electron is always a probability, and so it's always kind of there, but we don't know exactly where. If you want to know better where it is, something has to hit it to let the universe know where it is, and the universe will calculate where it'll be, give you a better picture where the probability is, but it still doesn't actually know where that electron is. Now, I gave you a couple experiments. I'll give you one more to play with, an idea here. In order to talk about has been around because it's such a crazy, nutty idea. Whose ideas to show us? So you got your electron here, and you put over here a kajillion volt potential. So you know full well this electron would have to have a kajillion joules to get over through this barrier. And so it can't, theoretically. The electron acting like, well, we don't know exactly where it is, so we're just going to make it. As it approaches the barrier, in fact, it can't get through. So here, as the wave gets closer, though, something very interesting happens. This part of the waves, on that, you've got something fun to play with. Why? Because the universe isn't keeping track of the stink. It's very likely it's over here. There's some chance it was over here. Separate it, and you take this box, say up to like the China, and you leave them. It's likely over here, right? If you try to if you, in most ways you could tell it's still sitting here, right? Then we use the box. What do you mean by that? You create higher and higher potential. You force the electron to know what's the natural reaction more likely to be over in this box, right? And you just keep squeezing and being here is all the chance of here is 76 miles apart. And in order to get there, it had to go through a barrier it couldn't make it through. And then pop open the box. You pop open this box or you pop open this box. When you pop open this box, you'll just pop open this box, by the way. The electron is here acting like a full electron. The electron's here. There's no chance the electron. And you can't make it go back, right? Because your electron is. This is called electron for 30 years. It makes no sense. Electrons enough energy to get through that barrier. When you do the math using the probability curve, I mean, it can't be here, but it could be here. It could be there, but some chances there. And then if you squeeze this side, you end up with it over here, which is disturbing and wrong and unjust. But it's the truth. And so therefore, physicists a time ago explaining how this can't be, because every experiment we do to try to prove it is, works. And so now we enter the realm of, what does this tell us about the universe? First thing it tells us is electrons aren't themselves the only thing that does this. Protons do, neutrons do, your average baseball does. What? Yes, you throw a pitch towards a batter. One of the reasons why a batter is going to possibly miss that, because there's no way to know where that is resonating. Yeah. Now here's the thing. Remember, the number is h bar, and it equals the change in x and the change in momentum. So the error in this, and the error question is, how big are these numbers? Well, it's times 10 to the negative 36th. And so therefore, we don't care. This is true. The baseball is fuzzy. It's not actually there. It's actually a wave motion. Everything is actually acting like a wave probability distribution. But the boundaries mean it's somewhere between a cajillionth of a meter this way and a cajillionth of a meter that way. I'm not going to miss it because it's going to pass here. Chances of that happening is almost zero. But it could happen. And that gets really interesting because that is a series of thoughts. All this stuff could happen. It just is extraordinarily unlikely on a really large scale. And then how would you observe such a thing if it did? That's one thing that we discovered. Another thing that's interesting is to explain this. What does the world actually look like where this makes sense? There's two explanations. One of them I'll give to you after we get done with relativity, because it works well with relativity as well. The other one is this idea that the universe is actually quantized. What does that mean? It means the universe looks like a, and that as we go, as Bob subatomic particle goes, it's in this spot. It doesn't ever travel between these two spots. There's no place between these two spots. It simply leaves here and goes here instantaneously. This, by the way, handles all of our problems, right? Because one of the things we can't decide what an electron is. Well, that's because once you get down to this level, you can't see how, because the electron could here or here. That's always going to be the case. And as long as you're waiting, it implies some other funky thing. Now, another thing this implies, argument, and that implies that when you have a planet, let's do a charged particle and another charged particle. This charged particle sitting in one of these holes, another one of these holes. We know that the force extends from one to the other. They're attracted to each other, right? Here's the problem thing between the two. How can you be attracted when there's between the two? There's nothing but holes. The answer is you must create particles that can travel and carry force. So this force particles from a visible rubber band that's standing between two objects. Force is actually a bunch of little to the other one and gives it orders to respond. Particle strikes the other one, it's attached to the other one, and the other one goes, oh, I get what I'm supposed to do. I'm going to, okay? Now you're thinking, okay, whoa, it's a big issue. We went looking for these. This was Albert Einstein's favorite idea. That's what we discovered. They're there. The easiest one to describe is light. Light is how charged particles respond to each other. Bits of light traveling between the two is what causes the force between them. And so therefore that one's really easy to understand. It is the natural force carrier for charged particles. When you look at strong nuclear force and weak nuclear force, which we've never talked about, but those are an atom, and also what causes it to have is equations that look like F equals blah, B squared. Okay, you're familiar with that. There's a constant and two numbers. Forces all particles with that charged particles. Force particles, okay, stick together, the nucleus fall apart. An occasion when it says, hey, get out of here, and it bounces it out. We've did these force particles. Oddly enough, the force is perhaps the one you should be the most familiar with, and the one we are most sure we should be able to detect it by now. We have some evidence of it, but we have no solid proof it exists. Gravity is disturbing. If you have two massy objects, mass, we have never detected the force particles between the two. Now, that's a little bit vague. There is some things that there are particles that seem to make things more and less massive. That actually carry the mass. Or this one, that's why things typically have 4 different kinds of masses. But the force particle itself has eluded us, and we're sure we should have detected it by now. So that's a little disappointing, and the theory had the pun. The last thing is the thing that's most going to keep you laid up at night, which has to be quantized. What does that mean? Well, remember back to we had a red particle. Okay, our red particle that goes from one to the other, that can over time. As they disappear for an period, means the universe is a series of events that just happen in 0 time. Now you're thinking, this got exploded, so I'm never going to think about this anymore. When you go to a movie theater, this happens to you every time. What? There's a series of pictures. Light through one, and they quickly change to the next one, quickly change to the next one. They change it to 60 frames per second. So does, by the way, refresh rates. Please don't, write your letters to me. That's fine. I understand. But 60 frames per second is the standard. Most people deal with the space in between. What happens is you see this slowly moving forward, and you assume if frame by frame, you'll know you're not actually of pictures. Since you're watching a series of pictures, that means what's actually happening is if this thing, and then boom, it's instantly here, and then boom, it's instantly here. What quantized space theory is telling us is that the universe, the universe only allows instantaneous snapshot frames. So in other words, the particle is here, then it goes to here, and we're taking pictures as we go along. Now, for those of you truly disturbed by this, I have some good news for you. The quantized space theorem almost assuredly has to have a quantized time. It has to, because of the reason we talked about it. It has to, if it can't be only one place or the other place, there has to be 0 time between the two, right? So that has to be so. The good news for you is this. We have not found this time thing. We have found hints of it. What are the hints? We've had falling under gravity. We know they're falling under gravity. We think we've got it figured out. And we have detected a particle hanging up. What does it mean? It didn't go to the next spot. Okay? Particle's falling under gravity here. When we go to measure it, it's not here because it's 1 quantum distance off. Now, there's a lot of reasons why keep 1 quantum distance off. A lot of them have to do with quantum mechanics. It's just probability. Guys, so I don't know why you're excited about the fact that this didn't work this time. It just took a picture, and the picture was, there's a 2% chance was the next hole, and it wasn't the next. It wasn't in the next. Oh, sorry, 90% chance the next wasn't there yet because quantum mechanics. It wasn't actually in the spot you thought it was. There's some chance it wasn't. Okay, so that's a possibility, but it is also a possibility that time is not in fact quantized. Okay, now I will give you one more theory at the end of relativity that also explains this strange quantum behavior. But we'll say this: most quantum mechanicists are more sanguine about it. What I mean by that is they just basically say, that's the way the universe works. No reason to explain it because our brains aren't really good at quantum mechanics. Okay, we might someday get better at explaining this sort of thing, but for the most part, I'm trying to explain something that we refuse to accept. We refuse to accept that the universe isn't keeping track of where my cup is. Why wouldn't the universe keep track of my cup? What's wrong with my cup? The universe doesn't care. unless you look at it or unless light shines on it or unless it falls off the table. That's the end of this one. I'll try to get you next.